My name is Julie Futcher. I'm a chartered architect and an independent consultant on climate responsive urbanism. My work explores the direct influence of urban morphology on access to passive resources, i.e., day, sunlight, and ventilation, and in turn, the net energy effects on the neighbouring setting. Taking the City of London, aka the City, as our case study area, we are undertaking a number of interconnected and ongoing research projects. Here I report on early research findings that provide an insight into the influence of built form on the wider environment. The city sits at the very heart of Greater London and is both its historic core and a world-leading financial district. Its location means not only does it have to manage its own conditions, but regardless of the prevailing airflow, must also manage the effect of the background conditions, i.e., from the rest of London. This image shows how built form varies across the city, with the black spaces representing open space. When we focus in on the city, we can see how both building density and building height increase. Research shows that at least up until the start of the pandemic, people enjoyed living in tall buildings. However, their impact on the wider environment is not generally addressed. Tall buildings are recognized to have a dynamic effect on the surrounding landscape, for example, loss of sun and daylight to adjacent buildings and the ground, alongside changes to street scale, ventilation, and, in turn, air quality. The magnitude of these built form effects on air quality is explored here. In the city, both the local and prevailing conditions have resulted in poor air quality. But what does this look like? From this photo, somewhere near the top of 22 Bishopsgate, looking west, we can just about make out important landmark buildings, such as St Paul's and the BT Tower. And looking east, where we can just about make out Canary Wharf. Traditionally, air quality data is gathered from collection points close to roads where concerns are raised. But here we are concerned with the impact of built form on air quality and focus on an area where we had previously conducted a series of microclimate studies. Without going into too much detail, we found that, in line with urban climate research, daytime air temperatures showed little variation between locations. The exception to this was around the base of tall buildings, where daytime air temperatures were lower and average wind speeds were higher. This suggests that tall buildings pull in cooler air from above the canopy top down to street level. These results informed the location of 80 NO2 diffusion tubes to see if we could capture the impact of this dynamic flow on air quality. Briefly, results demonstrated a close correlation between air quality, daytime air temperatures, and wind speeds, identifying locations with good air quality in areas of tall buildings and low levels of traffic, for example, the Eastern Cluster, Site 7, and areas with tall buildings and high levels of traffic, i.e. 20 Fenchurch Street, Site 8. 20 Fenchurch Street, the infamous walkie-talkie, can be seen here with its blanken used to dampen the effects of its built form on the solar beam. Another interesting observation is the comparison between Moorgate, Site 10, and Bishopgate, Site 4 and 7A. Both streets are major north-south thoroughfares through the city. But despite having similar levels of poor air quality, Bishopsgate is significantly more congested. Whilst this outcome is still under investigation, it is worth noting the difference in the built form of these two streets. Moorgate is a relatively symmetrical street, while Bishopsgate has considerably more variation in building height and street width along its length. It is also worth highlighting our validation study. Here, our measured data closely matches the CFD study undertaken at the beginning of the pilot study. Overall, the observations show that both tall buildings and street geometry have an impact on air quality. General observations indicate built form has a localized effect on air quality. The best urban air quality is found where there is both low levels of traffic and a cluster of tall buildings. Air quality at junctions is worse than those recorded nearby. Localized built form influences air quality at pedestrian level. Minor obstructions, such as construction canopies, can significantly affect air quality. However, at the city scale, both the local conditions and the prevailing airflow patterns produce areas of sustained poor air quality. Whilst results indicate that tall buildings can improve near-ground surface air quality, this is at a cost of hostile conditions at ground level. However, results are interesting for cities where increasing urban density and increasing building height is changing the urban landscape in such a way that the emerging morphology will have significant long-term impacts on outdoor climates and the ambient environment for other buildings. Currently, these remarkable changes are proceeding without any overall guidance or assessment of the aggregate effect. Instead, each building is evaluated on its own standalone merits, with little consideration for the wider impact on the surrounding setting. These issues are being explored through a series of edge debates titled Cities, Climate, and Critical Urban Infrastructure. These events bring together some of the UK's leading building and urban experts to exchange ideas and to develop policy guidelines that are appropriate to creating efficient, comfortable, healthy, and livable urban environments for now and the future. Please feel free to contact me for more details.